Example number 2, using logarithmic regression to solve a problem algebraically. In this question, we're actually going to solve it graphically, but this is just a good reminder that we can do anything algebraically. If we want to find out what a y value is, or a dependent variable is, we can just like plug into the equation, the literal equation, plug in the value for x, and then calculate it from there. But I tend to, since we have the use of a graphing calculator, I tend to like to use that. Caffeine is found in coffee, tea, and soft drinks. Many people find that caffeine makes it difficult for them to sleep. The following data was collected in a study to determine how quickly the human body metabolizes caffeine. Each person started with 200 milligrams of caffeine in her or his bloodstream, and the caffeine level was measured at various times. This is why I love Applied. Seriously, it is so cool. This is based on real data and interesting things like how fast does caffeine leave your body. So what I have done is I have already put this into the graphing calculator. What I'm going to use this time now is just to check it. So I'm going to go scroll all the way up. I guess I didn't need to do that, but we'll just start at the very beginning. Okay, 168, 167, 113, 145, 90, 125, 138, 77, 83, 50, 150, 55, 112, 84, 136, 180, 110, 75, 76, 49, 33, 80, 145, 100, 71, 156, 153, 130, 90, 112, 32, 23, 25, 45, 27, 18, 29, 43, 25, 21. Woohoo! So this is our L. I didn't mention this before, but this is our L1 and our X value. This is in our L2, and this is our Y. And this one keeps on going. So L1 and L2, just like that. Alright, so I hope what I'm doing, I know I'm taking up time here in the video, but I hope what I'm doing is I'm modeling the fact that you should be checking through all of your data before you do the linear regression, because you could lose marks for just like punching in one wrong thing. And since you're not necessarily going to punch in all the values or write down all the values in a table on your test, this is just a good way to ensure that you're going to get all the marks for that linear regression. So 19, and I'm now going to start here and work my way up because that's more efficient. So 19, 17.5, 12, 15, 20, 18.5, 13, 17.5, 18, 16, 5, 6.5, 4, 2.5. Now you're noticing with the 4, I'm not writing 4.0 because 4 and 4.0 is the same. 2, 8.5, 6, 3, 7.5, 14, 12.5, 9, 8, 5, 1, 3.5, 7, 5. And I'm just going to make sure that it's matching up. Yep, it's matching up with my 112. Good. 12, 2.5, 12, 7, 8, 3.5, 4, 6.5, 3, 5, 1.5, and 1. Good. So let's graph this thing. Oh, I'm just going to clear this because that's for my last one. I'm going to change my window settings. I'm noticing anywhere between 168, is there anything more? 180. So if I go to my window settings and go from 0 to, say, 200, that's going to be fine for my X values. And then for my Y, I'm going anywhere between 1 and 20. Okay, so if I were to change it from 0 to, I don't know, 30, just for good measure, we'll graph it. And we're noticing here that we have a whole bunch of data points looking like this. So I'm going to go quit this, and I'm I'm going to create my logarithmic equation. So it says right here, let's just look at the question. Determine the equation of the logarithmic regression function for the data representing the time as a function of the caffeine level. Determine the time it takes for the average person to metabolize 50% of the caffeine in his or her bloodstream. Round your answer to the nearest tenth of an hour. Paula drank a cup of coffee that contained 200 milligrams of caffeine at 10 a.m. How much caffeine will be in her bloodstream at 9 p.m. that evening? Round your answer to the nearest milligram, or mg. So let's just take a look at the units here. So milligrams is what our x's are in, and hours in times. Cool. So we're going to do this first. So I'm going to go Statcalc, and I'm going to scroll down. I mean, at this point I can just hit 9. Okay, that's what gives me my linear regression. That's on my calculator. It could be different on yours. So second, L1, comma, second, L2, comma, vars, y vars, enter, enter, enter. So remember, I'm going to do 3 decimal places for all of them, and it's the form y equals a plus b ln x. So y equals, now I'm not going to write down a, I'm going to say 44.393 because the 7 rounds it up. Minus 8.358 because the 6 rounds it up. ln x. I'm just going to see if I remember that right. Oh, yeah, not 3, it's 8.358. Yeah. Okay, so then this one is going to be perfect. Determine the time it takes for the average person to metabolize 50% of the caffeine. So 50% of the caffeine in his or her bloodstream. So we said here that each person took 200 milligrams. So that means that what's left in their bloodstream is 100 milligrams. And you want to find the time. And we want to the nearest tenth of an hour. So we're given, I'm just going to make this a little bit bigger, given in depth, and we want depth. So we're going to use value. So we go second, trace, value, x equals 100, and then my y equals, let's see, so I'm going to go second, oh, look at that lovely logarithmic function. Second trace, second trace, value, so x equals 100 milligrams, enter. Y is going to equal 5.9. 5.9. And we want to round our answer to the nearest tenth of an hour, so we got it. So we know it's in hours. So after 5.9 hours, so almost 6 hours, we still have half the amount of caffeine in our bloodstream. How crazy is that? Last but not least, Paula drank a cup of coffee that contained 200 milligrams of caffeine at 10 a.m. How much caffeine will be in her bloodstream at 9 p.m. that evening? Round your answer to the nearest milligram, okay? So we're going to round to the nearest whole number. So with this always messes with me, okay? So from 10 a.m. to 9 p.m., I'm literally going to write, okay, 10 a.m. So we're going to have 10, 11, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9 p.m. I always use my fingers to count this out or some kind of visual because, yeah, it always messes with me. Sometimes there are one more than you assume or one less. So let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 hours. So we're given our dependent. So the dependent, so y equals 11 hours. So what we want to use is our intersect method. So second trace Then we want to go intersect. Before I do that, though, I want to say my y2 equals 11. Otherwise, there's nothing to intersect. So I'm going to go y2, I'm going to scroll down to 11, see what that graph is. Ooh, I see both of them, that's great. So second trace, I'm going to go intersect. Enter first curve, yep. Enter second curve, yep. Guess, yep. So for when the hours equal 11, the intersection point here is 54.34. So if I'm rounding to the nearest milligram, it's just going to be x equals 54 milligrams. So you still have about 1/4, a little bit over 1/4 of the caffeine that you ingested 11 hours later. How crazy is that?